Okay. Get my mic ready. I think we're all set. All right. Welcome, everyone, to the Project Development Workshop. This is the 11th workshop in the Cal Poly Pomona CPP Hyperloop series. It's been a while. And today we're going to be talking about a lot of different interesting topics. If you've ever wanted to proceed and doing a project on yourself, or learning how to build a complete robot, or how to just what the process is like in general, this workshop will cover basically everything you need to know to get to a working model of a project and to do it to completion. The reason why this workshop exists really is because a lot of the time when people work on projects, they come up with an idea that's really cool, and then they go ahead and try to implement it, and then that part's called the execution process, and they just get stuck there indefinitely, and the project never gets finished, and they start a new one, right? And this kind of like project cycle has happened to me a lot of times too, and it's really kind of a art to try to get the project to completion sometimes. And so we're going to go ahead and go over some skills topics and soft skills techniques in order to have you understand what goes into developing projects, have you understand as to how to engineer it correctly, and get to the finish line. So the whole goal of this whole workshop series, really, the whole 11, 12 workshops we have so far, is to encourage you to build your own projects and to continue on yourself. So I think this workshop is going to be a really important one in wrapping everything together, in actually teaching you how a project should be developed. So the first thing we should talk about is the process, really. So what is the process in developing a project? How do you start and how do you end? And so, well, I already discussed this slide, even though I made it this morning. The process of developing a project, like so, or today we're discussing the process used to develop an engineering-based project from start to finish, and apply skills from different workshops to a single project. So just to give a background as to what we've done so far this semester in terms of workshops, we've done programming using Python. We've done circuit analysis and construction, which is important when working with hardware. We've done PCB design. So if you are moving from a physical circuit to a PCB and simplifying the footprint of what you're building, it's really useful. We did soldering, how you put a PCB together. We had some supplemental workshops or elective workshops on things like sustainable engineering, if you want to include that in your project design. We also had things like flight control, if you're working with drones, and how to know all the different parts of a drone. We also had Internet of Things, which actually hasn't been released at the time of this recording, but will be released after the last one, which is honestly a pretty interesting one as well, but technically complicated due to currently students working on IoT at Cal Poly Pomona not being able to access Add Your Own through microcontrollers. It's a security issue, really big deal, but also a really cool aspect of engineering. And also, we had 3D printing, which taught you how to manufacture your components and get it from a CAD model into real life. So there are a lot of different modules that come together in this workshop to completing an actual project. So we want to integrate components for functionality. So if you have a CAD model, per se, of some electronic case and the PCB, the integration process for combining those two would be screwing the PCB onto the 3D print. That's a really simple way of integrating it, but if you're working with more complex components, like motors, servos, stepper motors, and integrating it with like an Arduino, things become more complicated really, really quickly. We're also going to be learning basic robotics concepts. So if you have never learned robotics before, or are just starting out in electronics, if you're doing like building a robot project or working with some sort of like software and hardware integration, learning robotics concepts is actually really important. Even if you're not an electrical engineer or a computer engineer, you're a mechanical engineer. Every type of engineering or every type of STEM major or STEM topic should learn these concepts. And we're not going to go into like calculus or anything. So these are like surface level concepts that we'll be talking about. Oh. And also how to test and troubleshoot at work, because most of the time things don't work first try, unless you're God. But we're not. So things will go wrong. We're going to be talking about that. Okay, now we're actually getting to the real process. Here's where things get entertaining. Now, there are 5 stages to success, as I like to go about when doing my projects. And these don't have any like set names. They're kind of like just things I've named them myself. But the basic idea is there. The first stage is always the idea or the initiation stage. So it's when you actually get the idea to perform a project or have the initiation to start one. Most of the time, this step comes from identifying a problem you have in real life. So for example, if you always have to place your headphones on the ground and you accidentally step on them, then you could make a headphone stand that can hold your headphones up, right? The problem would be you step on your headphone stand and it breaks. Your solution would be to make a CAD model of a headphone stand that you 3D print out and use in real life. Another example, if my sink was broken, which it still is, and I can't wash my hands, then I would build a little robot to dispense water onto my hands from like an external source. That's my Alexa sink, which I still haven't fixed the sink. It's been 2 years. It's a process. Anyways, in stage one, these ideas are really easy to come by, right? They just require your brain. They don't require any external hardware or electronics. And a lot of times, you get ideas and problems for projects just by like weird places. Like I get my ideas a lot from the shower and when I'm dreaming, which is surprising, but it's true. Like I also solve problems in my dreams and I have to implement it in real life. It's kind of weird, but subconsciously solving problems is kind of like the idea. But a lot of times when you're like deep in thought, like in the shower, you'll randomly get an idea and start developing solutions for it, which is like really cool. So that's stage one. The next stage is planning and project management. Now, this is a step that a lot of people overlook because they don't know, or they just go straight into executing the project, right? You have an idea, you want to do it, you just go into execution. But you need to plan and manage your project before you start it, just so that you have a basic guideline on how the project should go on, right? If you don't have any planning, the project could spiral out of hand really quickly, right? You could use too much money, you could spend too much time, and just eventually get nowhere. So the more you can plan out your project from the start, the better. And we'll talk about some concepts you can use to do this. The third stage is execution or the build stage. This stage is where you actually build your project. You buy all the parts you need, you get them delivered to your house, and you start screwing things together, and you start making your product. Stage 4 is testing and troubleshooting. So after you build your product, it might break, it might catch on fire, it might explode, but it might not work as you expect. So in this stage, you'll need to find a way to test and troubleshoot your work. And the fifth stage is documentation and closure. Again, another stage that often gets like missed or not done because this stage, very few projects actually make it to. So if you think of it as kind of like a filtering station, this whole process thing, a lot of ideas will come into the filter and only a very few will leave from the end. So we want to get you all situated with this kind of process so that when you do a project, it gets to the very end where you have stage 5 documentation, you can publish your work, and then you can close out the project. This is a drone I made. And this drone basically was 2 years in the making. This drone did not work until actually a few weeks ago, in which I guess the project timeline for this drone was about 2 years. But during those stages, I first got the idea for building this drone by YouTube, actually. And I wanted to build that because it looked like a fun way to learn about drones, aviation, and robotics. Stage 2, I planned this project by creating a bill of materials and a Gantt chart to see how much money it would take me. This thing is about $1,000, by the way. Stage 3 is the execution build stage. This stage didn't take me too long, about a month or two. Stage 4 took me about a year and a half. People in the audience who know like this project that I'm doing, like know the troubles that flying drones actually would take. And it's kind of a wacky process because drones are hard. But documentation and closure is what I'm doing right now as to end up my senior project and to basically show the school what I've done or show anyone else I present this to what I've learned in building this drone. Just an example. Okay, let's talk about basic robotics. Now, you don't need to be, again, very technically intelligent to know what this section is about, because what we're going to talk about here is surface level concepts. We're going to go from it from a very basic level. So I've talked about the black box theory in multiple different presentations, but there's no better way to talk about black box theory than talk about it now. Because in essential, all projects follow this black box theory, right? In any project, you always have some sort of input, and you always have some sort of expected output. Or if the output's not expected, you're trying to find out what the output is, right? And the black box is going to be everything in between. So you're going to consider the black box. The black box is going to be things you're doing to get from the input to the output. So if you think of it as like a flow chart, your input is going to be things you already know. Your output is going to be things you might not know or might not understand. And black box is going to be everything in between. And a lot of these examples in this PowerPoint are going to be biased based on robotics because I am from a robotics background. But you could use this for anything else, really. You could use this for like a science fair project too. But these are the important questions. Number one is what are my inputs, right? Number two is going to be what are my outputs. Those two you gotta have to figure out first, right? If you don't know what specifically your outputs are, you can give a guess. You can give a range of possible solutions. Like if I was doing a science fair project on seeing if sunflowers can live in things that aren't water, like if I put a flower in Coke, will it survive? Right? My inputs would be the flower and the Coke. My output would be what happens to the flower and Coke. It'll probably die, but who knows? But I still gave an estimate as to what I would expect as the result of my project, right? If you don't have that expectation, it's really hard to actually understand where you have to go. And you get really easily lost when you're trying to connect the dots. So, again, third question is, how do I get from my input to the output? And what resources, knowledges, or skills are needed? This one's hard because a lot of the time when you start a project, the scope of the project is going to be way beyond you. So if I'm trying to do a project on, let's say, machine learning regressions, let me rephrase that. So if I'm trying to do a project on, let's say, mapping out the amount of trains that pass by this metro station in X amount of hours, or doing a study based on that. And in order to complete this, I find that I need to use a machine learning regression. I don't know how to do a machine learning regression, right? But it's something I'm going to need to complete this project with. So this is a very important question you have to ask yourself before you start a project, right? And I'll have an example on the next slide as to what you should answer this with. So for this question, you may use a flowchart or bullet point notes to complete the stage, but just generally, I usually have a document listing out all of these options whenever I start a project, just so that when I look back on the project, I have a good summary as to what's going on. Because again, this can also work as a really nice abstract. An abstract is just a one-paragraph summary that begins your project. Right. So let's go over an example. This is going to be the soccer bots for Cal Poly Pomona Hyperloop. It's a neat little device I made last year to compete in the robotic soccer bot competition. But we're going to use this to figure out exactly how I developed this pod and the steps I took to get from point A to point B. And using the model, what are my inputs? So in this case, my inputs are really going to be this controller, right? Because the user uses this controller in order to control the car. So everything stems from this controller here. If I can get a user input, or if I can get data from this controller to go to the car, then I can drive it, right? So the inputs are my controller and the joysticks and buttons. That's my starting point. My ending points is going to be what are my outputs. Now, this one's a tricky question. From the audience, what do you guys think the outputs are? Board got it. So basically, the outputs need to be physical in this case because it's a robot. And in this case, it's going to be the motors turning the wheels and moving the car, right? A lot of times people say, like, oh, the Arduino on the pod, the data on the pod, the car itself. But you want to be specific and see what you want to come out from the end. In this case, my inputs to the black box will be the controller. Outputs will be controlling these motors, right? Also, if you want the device that moves the ball as well, if you're thinking about pushing a soccer ball around the arena, you can also have that as an output, but I don't have it. So, well, continuing on this thread, how do I get from my input to the output? So how do I get the data to go from the controller to the car? And you can Google this step if you don't know how, or you can search on how other people do it, or you can ask a friend. A lot of the times I actually phone a friend just to double check my work for troubleshooting too. And so if you don't know how to get that from input to the output, I'll tell you right now. So the data on the controller travels to the RF antenna through the Arduino. The Arduino takes the data and processes it, and puts it to the RF antenna. And then on the RF antenna, the car receives the data. So the car will get the data from the RF antenna through the wireless communication channel. And then the car's Arduino will process that data and map it to the commands that the motor can understand, right? So it goes from the antenna to the Arduino does a bunch of logic, and then passes it to the motors. Now, I'm simplifying a lot of steps here because, again, we're looking at this from a high-level perspective, but when you're actually going deep into the code and mapping everything out, you can also use black box theory to make that happen, right? If we just minimize our scope to the car itself, in which the scope is the range that we're talking about, for the car, our black box is going to be the input being the data from the RF antenna, and the output being the motors turning, right, or the commands sent to the motor drivers. You know, in essentiality, you can use the black box theory to connect the dots between point A and point B. You can have black boxes inside black boxes, it's fine. But essentially, it's a good way for you to understand what's going on in a system like this. So what resources, knowledge, or skills are needed? After you figure out the top part, then you have to figure out, okay, what hard skills or technical skills are needed for me to complete this project? In this case, for the soccer bot, we need to know something like Arduino, C++ programming, wiring, and basic electronics. We need to know how to use this module. This is the wireless communication RF antenna, which is the NRF24L01. We need to know how to use an L298, which is the motor driver. And we need to know how to use basic power, because our car needs power, right, in order to move. So if we understand all of these, we'll be able to construct our own soccer bot. So that's how you should think about every system you do, even before you begin working with any hardware. So you got to do your research, right? Of course, if you already know how to do this from another project, you don't have to go through these steps. Like, I already know how to build a soccer bot, so I could build another soccer bot. But in case you don't, you can always just map it out in this nice little system here in order to get what you need. Okay, let's talk about control systems. So control systems, again, biased towards robotics because I'm in robotics, but if you want to build your own robot, you have to understand control systems. Control systems is a system in which the robotic component is controlled through. So if you have like a robotic arm, the control system is the method used to control the robotic arm, move it around, grip it, whatchamacallit. In understanding control systems, you need to understand the black box theory, because this diagram down here looks very similar to a black box, right? You have the input to your control system, you have your output, and you have the stuff that goes on in between. In the robotic arm example, the input's going to be signals going into the robotic arm. Output's going to be controlling the robotic arm, right, in different motions. Maybe the output could be robotic arm goes to a specific coordinate on a 3D plane. Your control system is going to be your code, your hardware, your software, and your firmware needed to get the robotic arm into that location. Now, there are different types of control systems for different specific cases of robotics. You have manual control systems, semi-autonomous control systems, and fully autonomous control systems. So depending on the scope of robotics you are doing, you'll have different control systems for each of them. So we're going to talk about that real quick. For the soccer bots that we made, remember that we also have feedback elements, so I'm going to cover this in a second. But for the soccer bot, we have the user input being a controller, right? We also call this a transmitter because it transmits signals to another device. And the car would be called a receiver. Now, this is known as an open loop control system, which also accounts for the manual control system. So if we are manually doing something to the robot, like controlling with the controller, we have to follow this kind of system. In this case, all actions are explicitly predetermined in the script. What I mean by this is all actions are going to be mapped from the controller to the car. We're not going to have any way of the car thinking of what to do on its own. Everything is just predetermined. The output is directly based on the input signal. So this flowchart on the bottom right here showcases what it looks like if, I think this is part of, this is just a generic one, in which plant is the thing being controlled. So if I'm controlling the robotic arm with a Arduino, then the robotic arm is going to be the plant. So here is what's going on actually inside the black box. We have the input that goes into the controller. The controller will send a signal. In this case, the controller might be an Arduino or other microcontroller units. It sends an actuating signal to the plant, which the plant is the robotic arm. So the Arduino sends a signal to the robotic arm, which can provide an output to you. Right? But in this case, the arm cannot think for itself. It doesn't have any feedback elements that feeds the signal back to the input. Everything in this system is going to be controlled by the input, right? It's not going to be able to think for itself. It's not ChatGPT just yet. So for a manual control system, this is kind of like driving an RC car, right? Because when we're driving an RC car using a controller, all the actions are determined by our controls, Nothing is determined by the RC car. For a semi-autonomous system, this one's a little bit tricky because semi-auto just means that we are executing a script and having the car follow it. So if I gave the RC car several instructions on what to move, like let's say drive forward for 3 seconds, drive right for 2 seconds, drive forward for another 5 seconds, that kind of action is explicitly mapped out inside the code so that everything goes from the input and goes to the output. So that's semi-autonomous, in case you want to write that inside the code. Now, a closed-loop control system is a little bit more difficult in explaining because you have what's called a feedback element going back into the beginning. So this is known as a closed-loop control system, or also, if you have done any sort of complex class, it's also known as PID control, or you can use bang-bang control or proportional control. It's a way of optimizing a certain point in your control system. So the first thing you need to do when you're working with some sort of autonomous code, and by the way, this can be things like a self-balancing robot, or this can be like a drone, right? Because a drone needs to hover in the air and balance the signals to all 4 motors to do so. This can be like even the Hyperloop pod, in which I have ultrasonic sensors on the ends of it to prevent it from slamming into the walls. So any of these cases would be a case in which I need to find out what's optimized, right? In the event of a self-balancing robot, the optimal point will be the robot balancing itself and not moving. So in this case, it would be the gyroscope returning an angular velocity of 0 on all 3 axes. The drone, in this case, would be the same thing. We want it to hover. That's the optimal point. So any error that gets generated from this drone will be based on the inertial measurement unit. It'll be the angular velocity not being 0. And for the Hyperloop pod, we don't want it to slam into the ends, so our optimal point will be, let's say, an arbitrary number of 15 centimeters from the end. Again, this can be changed, but in our pod situation, because we want to protect the sides, I'm just going to set the borders to about 20 centimeters, or 15 centimeters. Again, arbitrary. So when you have a control system and you have any sort of error, an error is any kind of arbitrary number that takes the system away from its optimal point. So for a self-balancing robot, the error will be, let's say the robot is tilted 45 degrees. The 45 degrees is going to be the error, right? And that's what you have to correct in the code. So for the feedback elements, when it feeds it back into the input, there's going to be a calculation made here. That's what this X is. This is going to be the error signal that either adds or subtracts from the input in order to feed it back into the controller and into the plant. This kind of loop here runs continuously over and over again until you get an optimized standpoint, or if you get the optimal condition. And this loop runs over and over again. It does a bunch of calculations just to make sure your self-balancing robot can balance, your drone can fly, and your Hyperloop pod doesn't crash into a wall and die. So again, a new controller signal in this case is calculated and it feeds into the output. So every single time this loop runs, it runs a calculation. Whether this calculation is going to be a simple linear equation or a very complicated differential equation, doesn't matter, a calculation's made. After that calculation, a number is either added or subtracted into the inputs and fed through the system again, just to make sure that you have an optimal output. Now, most of the time in a closed-loop control system, you will need a feedback element, which a feedback element is usually in the form of a sensor. So sensors that exist in the world for at least cars are kind of like ultrasonic sensors, IR sensors, inertial measurement units, right? Inertial measurement unit is a fun one because it measures movement. So it measures the acceleration of an object or the angular velocity of an object. Again, I'm saying angular velocity a lot because that's what we use to usually balance these robots. But there are a lot of sensors out there. And the sensors will keep measuring things from the system that you can feed back into the input. So in this example, this is supposed to be a GIF, but it's not playing. So what is the processing system on a robotic vehicle? So when we're thinking about systems again, in this case for the Hyperloop pod, the processing system is going to be like an Arduino. And an Arduino is a little controller board that can have inputs and outputs from it. It's kind of like a smart computer on a pod, although you shouldn't call Arduino a computer because it can't run any operating systems. It's kind of a dumb device, but also very smart at the same time. It's a paradox. So in this case, the Arduino on the pod and the Arduino on this controller are going to calculate things in order to make our system work correctly. For an input, what type of inputs would an autonomous car require? In this case, we're talking about things like a controller input, although that's manual, or if you want fully autonomous systems, you would have things like LiDARs, IMUs, ultrasonic sensors, as you can see this one on here, or maybe IR sensors, things that can basically give the robot an understanding of where it is in time and space. A camera would also be great, right? Then you can teach the robot what things look like around it. You can map out a distance for it to travel on like a virtual system. It's very, very useful. Again, for a robotic car, what outputs would the car need to control? What are the outputs in this case? Yeah. I got to make that point because actually these slides are from another course I teach. And so it was, I would say, a little bit difficult to get them to understand that first point. But again, the motors are the outputs. It's very simple because in an autonomous car, you either have the motors or the turning servos, and that's probably it. But everything boils down to that, right? You're not going to control anything else unless you put like a rocket launcher on a car. But in this case, it's very simple. You don't have to overcomplicate it, and the outputs are just the signals you send to the motors or the turning servo in order to get the car to run. In this case, literally all the outputs is the signal I send to these motors to get them to turn. Very simple. And in this case, again, feedback elements are going to be the sensors on the pod. So in this example here for the Hyperloop pod, we have the ultrasonic sensors that prevent the pod from crashing into the end. Also acts as a great braking mechanism. That way that if it senses that it's about 15 centimeters to 20 centimeters away from the end, then it will just turn the motors the other direction. Right? It's pretty simple, self-explanatory. Okay, now we're going to get into kind of like how to build a robot. And this is more technical than what we just talked about, but it's also very important to understand. I talked about this last time during Flight Control Workshop. I'm going to say it again just because it's so important. We're going to learn how LiPo batteries work. And LiPo batteries are lithium polymer batteries. Almost everyone here knows what a 9-volt battery is, and some people might know what an 18650 battery is. It's those batteries used in cameras. But compared to 9 volts, 18650s and LiPo batteries are very volatile. They're very dangerous. And if you use them incorrectly, they can either catch on fire or explode. So generally, LiPo batteries are made of different cells. In the picture here, you can see a 3-cell LiPo battery, or a 3S LiPo battery, that's connected using this little, I think this is called a T connector, in which it's connected to the positive end of one of the batteries and the negative end of all the batteries. You can see these batteries are connected in series, which means that the voltages in each of these cells adds up to a certain value. Now, cell voltages, in which we have to be concerned about, if you buy a LiPo battery off Amazon, every single cell in this LiPo battery will have around 3.5 volts. This is known as the storage voltage. And the storage voltage allows this battery to be stored at a safe value such that it doesn't blow up or corrupt as easily. The worst thing you can do to a battery is leave it either at too full of a voltage or too little of a voltage. Because too full of a voltage, and it will start expanding and bloating, kind of like how if you eat a lot after dinner and go directly to sleep, you will feel bloated when you wake up. Or if you store the battery at a lower voltage below 3 volts, it will start dying off. Basically, the battery will not be able to hold enough charge the next time you want to use it. It kind of explains why whenever you have a computer and you use it for a long period of time, the battery will start decreasing after a while and become like less and less useful. In this case, my computer is actually facing the same thing right now. It's like really bad battery life, about an hour and it dies. But LiPo batteries are really important to understand because it's the cornerstone of a lot of robotic equipment, right? Almost all robots come with a power source, otherwise it can't run. And so, again, safe voltage is going to be 3.5 volts. That's the storage voltage, and if you're not using a battery for a long time, you should always keep it at that. The maximum voltage that the battery can hold, though, is 4.2 volts. So for a 3S LiPo battery, what's the maximum voltage it can hold? Quick maths. So it's pretty much just your 4.2 per cell. There's 3 cells in series, so you just add on them together, right? So it's 12.6. So when you're calculating LiPo battery voltages, that's what you have to look out for. So in this case, what is the storage voltage going to be? If I buy a 3S LiPo battery off Amazon right now and test the voltage, what am I going to see? let's check it out. So actually, in my bag, I have a newly bought battery from Amazon that just came in the mail this morning, and we're going to go ahead and test it out right now and see what the voltage is. So, you can see here, no, this is not it. Okay, so this is a new battery that I just bought off Amazon, and in my LiPo bag here, I have a lot of different ways to test the voltages of these batteries, including a multimeter, and also this cute little device. So I'm going to go ahead and plug the JST, and this little pin is called a JST. It connects to every single cell to test its voltage, so it can tell you the voltage of each cell. So I'm going to go ahead and connect this in, and this device is kind of like a multimeter for LiPo batteries. It has a really loud buzzer on the top, so I'm going to cover it just to like protect your ears. But to plug it in, I'm just going to plug it in like this. Nope. Okay. 11.3. So it's a little higher than storage voltage, but you are right. It should be 10.5 when I get it out of the pack. I don't know why it's a little higher. That's weird. Because if it's stored like too high or too low voltage above the center, that means it's not properly stored, and it will start to deteriorate over time. It's kind of like, decharging is kind of like the idea of freezing humans so that they can live longer. It's kind of weird, I don't know. But again, 3.5 is safe, 4.2 is max, and if each cell goes below 3 volts, you're in danger, right? You're in danger of damaging the battery. For a 3S LiPo battery, what would be the danger voltage? 9, right? So if you see a 3S LiPo battery go below 9 volts, danger. Okay, let's talk about charging and discharging rates. So the charging and discharging rate is located on every single battery. It's usually a number and then C, right? So in this LiPo battery, I think this one has about 50 C of discharge rate. But the way you calculate charging and discharging rate is very important because it can determine what the battery's characteristics are. So let me get up this battery again. This battery is an Ovionic air battery, and it has a 22,000 milliamp hour capacity. So a lot of times batteries are measured in their capacity, which is the amount of milliamp hours you can store. So this is 2200. In this case, this is also a 35C battery, which states the discharge rate of the battery. So the discharge rate, or how many amps it can push out at a time, is calculated by multiplying the capacity and the C constant. So in this case, 2200 multiplied by 35 is going to give us the discharge rate in milliamp hours, which I don't know what that is, but I'm just going to round it to 2000, which is going to be about 70 amps of discharge. Camel's blank pen. So this battery can pump out around 70 amps. So if you're powering something like a drone, which is very power consuming, this is perfect for it, right? Let's go ahead and analyze this battery. This battery is a 6S LiPo battery, which has a capacity of 1000 milliamp hours. And you can be able to see that the battery size is relative to the amount of capacity it can store. The larger the battery, the larger amount of stuff you can store. Like this one is going to be a 5200 milliamp hour 3S LiPo battery. This one's a 1000 milliamp hour LiPo battery. So the size difference is really incredible, but you can use both of these to power devices. This one's a 6S LiPo battery, which means it has 6 cells, which means 6 cells connected in series to each other. The discharge rate for this one is going to be 130C, which means that this tiny little guy can pump out about 130 amps into a robot, if the robot needs it. Which, this one's my most powerful battery. I love it. But it's out of stock now, so I'm sad. Okay, so now that we covered charging and discharging rates. Discharging rate is the amount of amperage it can pump out one time. Charging rate is usually what you should charge the battery at. And for a lot of these batteries, they usually have a 1C charging rate, which means you should charge it based on the capacity divided by 1000. Or sorry, divided by 1. Because this is a 22 milliamp hour, so you should charge this battery at the rate of 2.2 amps. This battery is going to be a 1000 milliamp hour, so you should charge this battery at 1 amp. This one's a battery at 5.2 milliamp hour, so you should charge this at 5.2 amps. Usually, the charging rate is going to be way lower than discharging rates, but it specifies at what rate you should charge this battery at. So for this one, it's going to be 5.2 amps, 1 amp, and 2.2 amps. For Zoom people, I'm holding up different batteries and showing them off. For a lot of these components, you got to carry batteries in this flame-proof bag, because in case the battery catches on fire, it won't catch fire on things around it. This is flammable though, so battery bag. Usually these LiPo batteries have XT60 and XT90 connectors, or a T-plug. These are usually the most common ones. There's also XT30, and they come in all different shapes and sizes. So you usually want to connect LiPo batteries to the rest of your car or rest of your vehicle. Now the next slide is really important, because now that we talked about LiPo batteries, you guys might be really interested in taking this and just connecting it to a robot or an Arduino. And let me tell you, if you connect this to an Arduino, the Arduino will explode. It's happened to me before. Don't try it. So Arduinos usually can't take in a high amount of voltage, as you can see in one of these batteries. This is a 3S, so the maximum voltage is 12.6. Anyone know how much voltage a Arduino can take?
I think it's 9 to 12.
It's 9 to 12, but 5 is the safest. So if you plug in like 9 to 12 volts for Arduino for a long period of time, it will start like not liking it and heating up. 5 is the safe amount. So in order to regulate power to our vehicles, we need to use one of these options. We can either use a BEC, which stands for a battery eliminating circuit, or some buck converters, or boost converters, or UBECs, or power modules. All of these modules will separate the Arduino from the rest of the system. It will separate the amount of power coming from the battery from the rest of the system, which is probably going to take a large amount of current. So what happens usually is you take a battery and you split it off into 2 steps, right? You split one end of the battery off into powering an Arduino, and you split the other one into powering high power motors. Because think about it, in a robot, the motors usually draw a lot more current than an Arduino, right? Arduinos draw around 70 milliamps, and motors draw around 20s of amps, right? So you want to make sure the current that the motor sees isn't the same as the current that Arduino sees. Otherwise, that would be very bad, because if something shorts on the motor end, the Arduino is going to get shorted as well. So to separate this, or to eliminate the battery's effect on the Arduino from the motor, you're going to use a BEC. This safely regulates power from a higher voltage to a lower voltage, and there are a little bit of options you can use. Buck converters, or DC to DC buck converters, takes voltage from a high standpoint and converts into a low standpoint. This one actually is a combination between a buck and a boost converter. A boost converter is a converter that turns voltage from a low standpoint to a high standpoint. Usually you use boost converters for things like really small vehicles in which you attach a 3.3 volt LiPo battery to. Because a 3.3 volt LiPo battery is not going to power any sort of electronics, right? It's not going to power like an MCU. Right. So in this case, if I plug a 1S LiPo battery, which is a 3.3 volt LiPo battery, into the system, I'm going to need a boost converter to turn to 5 volts so the Arduino can be powered. You can also have a UBEC or a power module. UBEC stands for Universal Battery Eliminating Circuit. This is usually used for drones. This one also is usually used for drones. And this one's a fun one. This one combines both the buck and boost converters and allows you to either scale the battery up or down depending on this potentiometer. Either case, though, you also have to be considerate of the amount of current you draw from the batteries, and you have to be considerate of the amount of current that this module can hold. This one, I think, is a 3 amp limit, so if you want to draw any amount of current over 3 amps, you either have to put these in parallel or get a better buck converter or a transformer. Okay, I'm going to skip the next few slides because this is going to be next week's material, and I am running out of time before the activity. So generally, these topics are going to be very useful for developing a project which has a robot in it, but you can look at the 4x12 workshop for it, and we'll talk about more then. You can use LEDs in your project, you can use motors, you can use motor drivers, which this is all, again, really biased because I'm basing this off of what I talked about beforehand. And then project management. Okay. Back on track to really important things that we have to do. Hello. So, you're doing a project, you're really good at technical skills, but you suck at soft skills. So what happens? Your project gets out of hand, you spend too much money, you spend like too much time on it, and you get nothing in return. Your efficiency is crap. So, in this section, we're talking about the soft skills that make projects possible. First thing, bill of materials. Every project should have a bill of materials or some amount of money you have to spend on the project, because, you know, I like to say for a lot of projects that really, really matter, you have infinite budget, but in reality, Nobody has infinite budget. So you have to be considerate of the amount of money you're spending. So either you're building a Hyperloop pod, or you're building a drone, or you're building some other like small robot. You want to make a bill of materials to see exactly how much money you're spending on the project before you start it. And the bill of materials has a couple parts. It's important for managing funding sources, objects, and materials. So in a soccer bot, for example, you might have a funding source for the chassis of the car, which is a structure component. Or you might also have a type for electronics. You have to spend money on electronics. Or you might also have a component for decorating the car. So all of these are different components or different sections of a bill of materials you have to include. Usually BOMs are managed in charts forms. So BOMs, make sure you don't overspend on the project, because honestly, I do that way too much. I say to myself, I'm going to spend $500 on this drone, and it's going to be a really nice drone, and then I burn some motors, I burn some ESCs, I have to replace parts, and then it turns out I spent almost $2,000 on a drone. True story, by the way. So, again, bill of materials is really important. It's also really important for helping others replicate your project as well. In case people want to replace my drone, or build my own drone, or build a Hyperloop pod, they need to know what they should buy or what they should make in order to get it. And so if I give them the bill of materials, they're able to take it and buy everything on that list and put one together. So again, really good for documenting your work as well. Also, if you're submitting your project for grants, sponsorships, or other money sources, bill of materials is really useful because it shows everyone else that you are resourceful, you are prepared, and you are reviewing your contents so that you can go ahead and successfully complete the project. Because again, at the beginning of this PowerPoint, we went ahead and talked about the fact that a lot of projects don't actually get completed, right? A lot of projects will go into the very late stages of development, it'll go into testing and troubleshooting, and then people will just give up. Happens in senior projects a lot, because you only get 1 year. So this is why project management is really, really important. The last point is, if you're submitting for like a grant, allow for leeway. If you're designing a bill of material source, allow for leeway. Because, again, you might break something. And if you break a motor and have to replace it, and you use all the money you have for the project, it's going to suck because you're not going to have a motor. So again, make sure that your bill of materials is very well written. Also, I gave you guys a template. This is actually a template I have for Hyperloop Mini as well. But this is a really good way of outlining what you need and what you want. So BOMs usually come in table format. The columns represent different aspects of your project, and the rows represent different items purchased in the project. You will have things like your part name. So what you're going to buy, let's say if you're going to buy like a buck converter, you're going to put buck converter here, or an Arduino, or a motor, or a chassis plate, or 3D printed parts. Every single part name needs to be listed in the part name column. And then the next column, which is going to be the part description, is where you describe that part in detail. Because I'm going to tell you that I've made a bill of materials before without this part description, and then I go back on it, and it's just like this really long string of random characters and numbers that represent a specific chip on a PCB. And I'm just like, what the heck is this, right? Because it's just a really weird part name. So make sure you put a part description. Again, it'll help you later. It'll help other people later. It's really useful for a project. The cost of part is also very important, right? I have a link column here for me to put a link to the thing, but also parts per order and price per order. Parts per order is how many parts are actually in the actual system. So usually on Amazon, if you're buying buck converters, they don't come as one buck converter. They usually come as like packs of 10 for some reason. So in this case, I'm going to put 10 parts per order. So in the future, when I'm minimizing my bill of materials and getting it ready for documentation, I can go ahead and say exactly, I'm only using one buck converter, so I'm just going to take the price and divide it by 10. And it's going to be a very simplified model of my parts list. You can also have things like quantity, net cost, and also a total down here, which includes tax. So this is just a good template, and this net cost column here is all filled with Google spreadsheet equations, such that it will automatically calculate the total for you. I put a template on the slides. If you visit it, you can go ahead and copy it and use it for your own needs. This is a template that I've used for pretty much all my projects, so it's pretty reliable. The next thing we're talking about is Gantt chart. So other than money, the other most important aspect of a project is time. What's the amount of time you need to spend on a project in order to get it to work? All projects fall on a timeline. So whether you like it or not, time is going to pass. Like, unlike money, you might not need money to do a project, but you will need time. Gantt chart is important for mapping out the timeline of your project and working in teams and meeting deadlines. The second one is more important. If you ever work in a team, you might need a Gantt chart more than others. But essentially, it's really good for making sure you spend like 1 month on a project rather than a year and a half. Because again, with my drone project, that took me almost 2 years. It also ensures a higher chance of completion for the project. If you're prepared and reviewed, and you have a document showing that you have a set schedule for your project, it's more likely that you yourself are going to complete it, rather than just like leave it on a table to dry. You can also use this for submission for grants. I've recently been applying for different grants, and they do ask for kind of like documents to support the feasibility of your project. Gantt chart is a good one to submit for that. And again, allow for leeway. Again, things might go wrong. So if something explodes and you have to replace it, you have to make sure there's something on your Gantt chart that allows for that extra time for you to get that part and replace it. Otherwise, if you're just doing everything like on a very strict deadline, you're never going to get it complete. This is what a Gantt chart looks like. It's the template I use for every project again. So I'm just open sourcing it and allowing everyone to use it. This is a 2-part table format. Usually Gantt charts come like this, where the left side is going to be what you have to do, and the right side is going to be when you have to do it. So what you have to do, when you have to do it. You first start with your task name. So your task name is going to be a short description or phrase as to what you're completing for that project. So for example, different task names could be like integrating Arduino code with hardware, or testing to see if the motors work, or screwing in the controller together, right? Different things that you are doing as a part of the project in order to keep track of your timeline for it. Then you have assign to. Now, if you're doing this project by yourself, you don't need this column. But if you're working with others, you usually have a column here that states whether or what someone's doing at what time. And then you also have a checkoff. So if someone completes their task, you can go ahead and click the box, and it will go ahead and light up, and you can complete that task. Due dates are important as well, because just to make sure you're completing it on time. And a schedule map. Again, the when you do it part on the right is really important. There's a lot of tiny cubes here, and usually what you do is you highlight them in like red or green, depending on if they are completed or not completed. And you can go ahead and select the dates that you want a task to be completed by, and just like fill out a row or a few cells to represent that. And this kind of like right side is continuous. So you can see every single section here represents 1 week. And this project that I'm representing here goes on for 12 weeks, so there's like 12 of these lines. But again, it's a really good way if you complete this Gantt chart. Usually it takes like an hour to 2 hours if it's a big project. If it's a small project, it should take you no longer than 15 minutes. But completing this will ensure that you have a good track for completion, and that you complete the second stage, which is planning and management. Oh, here's the template. If you want to go ahead and complete this, template's there for you. Okay, before we go into the next section, my throat's drying up, so I need water. The next slide is going to be the downfall of a lot of projects. And I'm going to talk about it because Zach, who was originally supposed to host this workshop, is not here today. And we've talked about this with him a lot too. He's probably going to talk about this if he were here. There's a reason I'm putting foreshadowing on this. Okay, on the list of reasons why projects fail, feature creep. So, you are completing a project, and you're building the Hyperloop pod, and you're thinking, hey, wouldn't it be cool to put a robotic arm on it? No reason at all. No reason at all. And you're like, okay, let me put a robotic arm on it. And then you go, hey, wouldn't it be cool to make it so that it doesn't ram into the walls and put ultrasonic sensors on it? Or maybe put a camera on it so it can see what it's doing, right? Or maybe put some extra receivers on it so it can measure data from the battery on here. Or put some PID control so that it's like intelligent and moving. Or maybe even make some track that turns the pod so it can move on its own. This is feature creep. So feature creep is introducing things to your project that aren't really necessary for the scope, but they are there to make it look cooler. And for this case, I actually did need the robotic arm. That's why I put it on there. I didn't just buy a $1,000 robotic arm to put in this pod. I mean, I would love to. Again, ideas are cool. So features creep is excessive ongoing expansion or the addition of new features in a project. So whenever you're doing a project, you always have to keep in the back of your mind the scope of the project, right? What is the problem you're solving? How are you going to solve that problem? And just end it there. If you have extra time in the project, of course you can improve it. But most of the time you don't. Most of the time, you just think of an extra idea that would be cool to add to your project, but you can't ever execute it because A, it goes above your budget, and B, you don't have enough time in your Gantt chart. So you have to be careful about feature creep. Because feature creep will get you. Again, $1,000 robotic arm. So it will cause you to have an involuntary increase in funding required. You know, if you're going to add another feature onto like this pod, or if you're doing software development, add another feature onto a website, it's going to cost you more money. And not only money, time too. As they say, time is money, right? So it's also increased your time. Like I said, you don't want to spend more time on this project than you have to, so you have to make sure everything's in check. And also inject redundancy into the project, because let's say that this pod is supposed to carry a payload from point A to point B. That's it. If I put a robotic arm on it, I'm complicating that task, right? Because it doesn't need a robotic arm to carry something. It can just sit on the pod. So that's called redundancy, where you don't really need it, but you know, you have it anyways. So again, example, Hyperloop pod. This pod was changed into a battery swapping mechanism for drones later on down the line, which explains all the additional like attachments to it. But again, there's a lot of features on this thing, and if you don't stick to the main problem-solving points, you're going to run into many, many issues down the road. So again, how to fix feature creep? Define the scope of your project. Again, scope is going to be the range that your project covers, or the amount of area that the project will solve. Write down the scope of your project or tell someone else. A lot of the times, if you write down something, or if you tell someone else, something in the brain just goes, okay, I'm committed to this now. Like I'm not going to stray away from it. So a lot of the times for projects, I will usually tell someone else my plan, just so that I won't, forget it down the road. You want to make changes only when extremely necessary. This is an important point, right? Because necessary changes could include things like parts broken due to excessive current, which actually happened to this car. I exploded 2 motor drivers and 1 ESC before I figured out the power situation. Parts not fitting as originally planned. Then you have to come up with plan B, right, in order to make something that fits. Or you have to increase the battery size due to insufficient power supply, right? The original plan for this pod was to be powered by a 2S LiPo battery. Now that you all know what LiPo batteries are, I can say that. So a 2S LiPo battery is not enough to power the motors on the car, so I upgraded to a 3S LiPo battery. This is technically feature creep, but it is necessary to solve this problem, so that's why I did that. Okay, the next issue or fallacy for projects is the Ringelmann effect. Especially very, very common in colleges or industry situations in which you have a manager for your project. The Ringelmann effect applies to teamwork in projects, and it's the situation in which if the group size increases, the working efficiency of each member decreases, or the working efficiency of each member is imbalanced. So this graph on the right here shows that if one person is working on the project, they may put in 100% effort. If 2 people are working on the project, they may each put in 93% effort each, right? So it's not 100% anymore. And if 3 people are working on the project, they might each put 85% effort. So when we're talking about efficiency, we're talking about the amount of product we can achieve in the smallest amount of supply or resources given to the project. So if you have more members of a project and you don't have enough things to give them to do, or the amount of members in the project don't have enough, I guess, time or commitment, and they're just there, this is actually known as social loafing. That's the official term. I like to call it leeching, but it's a very more detrimental term to call for this kind of activity. It's just when you have members in the project that aren't doing what they're supposed to, or aren't contributing as much as others. And sometimes it's not their fault. Sometimes it's just the fact that the project is too big and there's no management. Because if you're doing a project by yourself, you don't need management. You're the manager yourself. So I'm going to go ahead and create my own product, manage my own time, do everything myself, and I don't get any complications there. You start adding more and more people, then you need a team manager or a team lead to coordinate everyone, right? This puts more work on the team lead. Maybe people are hard to communicate with, and just in general, if you don't have enough tasks to give them, then it just becomes a situation of people just being on the team because they're on the team, right? Again, social loafing. If you have this, it's basically lower effort contributed per person. You're not maximizing the efficiency of your project, and the project just goes on slower than usual. It's like, again, do you really need 10 engineers to change a light bulb? Probably not, right? Probably not, right?
Have you seen some of the light bulbs on some of the lighthouses?
Well, like a commercial light bulb you put in your house. Do you need 1,000 engineers to change a light bulb? We're increasing the number here.
Is the light bulb in space?
I mean, so you may also need to expand the scope, which again, if you have to modify your scope in any way, shape, or form after you create the project, it's a bad idea. All right? So I'm in a couple of senior design projects at Cal Poly, and some of them are large, like 72 people large. With large senior projects, again, it becomes hard to manage and coordinate everyone. It becomes difficult to communicate with people because sometimes they won't respond to emails. And you need management teams. Because when you start getting large senior projects, like 72 members each, you're going to need teams for like different members of people and different teams for what they're going to be working on. And sometimes these team leads are so affected by the managing and logistical part of the project, they don't actually get to experience working on the project themselves, which is why kind of management positions are stupid. Which is why I don't like large senior design projects. But some of them actually do make it work. Some of them are actually successful. And that's because a lot of the times people work day and night really hard on the project. And I do know some projects here at Cal Poly that are like that. But again, if you have too many members working on the project, like my own sub-team for my drone project is 30 members. So really hard to control. So it just decreases the efficiency. And you have to watch out for that kind of effect. Again, not just applied for senior projects here at Cal Poly, but also industry projects as well. If you ever worked in a large team, you'll probably know what I mean. Okay, now to go on to the section about testing and troubleshooting. And this is just to give you a brief overview as to what you can expect when troubleshooting projects, because a lot of the times, it's not going to be obvious as to what goes wrong. Oh, other times it's going to be very obvious, like when you plug something in and the motor explodes. Very obvious that something went wrong, right? But things can go wrong. That is a power outlet on fire. So whenever something goes wrong, it's usually because it's not what you expected the outcome to be. And in this case, definitely not. Like, I don't expect to make, unless I'm going out camping or something, I don't expect to make a fire out of an outlet anytime soon. So ask yourself, what went wrong? And most of the time, it's user error. Most of the time. Actually, like 97% of the time, it's because you messed something up. You short-circuited a wire, you soldered two joints together and created a short that caused something to heat up. It's usually your fault. Otherwise, faulty parts. So if you get a part from Amazon or AliExpress that might not be suitable for use, it's faulty and it's just cheap parts that you buy. So sometimes it's this, and sometimes it's also faulty code. So if you code something incorrectly and you send out a wrong signal to the Arduino, it might loop back to itself and create a short. I don't know. So how do you find these errors and fix them? I've boiled it down to like three techniques, but there are a lot of different ways to solve problems and a lot of different things you can do. The first thing is process of elimination. You eliminate different parts that you know are working and focus on the things that are not working. I know that's a really general explanation, but it's the way to go, really, just to figure out what works and what doesn't. Also, there are testing procedures that you can do for both hardware and software material that can help you solve the problem. This is a laptop on fire. So hardware testing wise, if you're working on a hardware like a robot or a PCB, You can use a multimeter to do voltage and continuity tests. Continuity tests are the most useful thing on the planet because they tell you if electricity can pass through a wire. If you use a multimeter, set it to continuity mode, and put the two ends of the measuring sticks across a wire, it should beep. And that beeping indicates that electricity will pass. A lot of the times, if your wiring doesn't work or it's not what you expect, like if you try to turn on a motor and it doesn't turn on, sometimes it's because the wire's loose. And if the wire's loose, of course, it's not going to turn on. So you can use continuity testing to see if the wire's actually getting sent through. Also, you can use a logic meter for signal testing, but that's a little more advanced. You can use an LED to verify that the signal is passing through. For software, you can use print statements, which are like the bane of existence for a lot of software engineers. Or you can also go into the serial monitor and the OLED display and check out what's going on there if you're working with Arduino. Come on. Okay. Process of elimination. This is a guy trying to fix a laptop that's on fire. And this is a very unrealistic situation, but stock photos, am I right? So,
I'm pretty sure I've actually seen you in that situation. On stream.
I have been in this situation on stream, yes.
Like, so unrealistic is really relative.
So, cause and effect wise, almost all problems have a cause. So what do you do to mess it up, right? So you need to technically understand each component of your project, maybe look at a data sheet, maybe look at some source to understand why this project or problem has been caused. Because again, most of the time it's user errors. You're hunting for the cause in this situation. Another way you could fix this is you can brainstorm all the different types of problems that could occur, write them down all on a list, and start checking them off if they're not accurate, right? Because eventually you're boiling down to like one problem that's the case. You cross them out if they're not successful after testing. So, two methods of solving problems. And the third one's my favorite. But you shouldn't do it all the time. So you can phone a friend that You can phone a friend to ask them to help you solve the problem. And sometimes that actually works because two brains are better than one. Do this way too much, though.
The biggest thing is sometimes the only thing that is the problem is that you didn't say it out loud. Sometimes just by talking about it, sometimes just by saying what you're thinking, you clear up what you actually meant to do and you see what the problem was.
Yeah. To clarify about this point, like, the friend doesn't have to be technically knowledgeable about the project, but I've phoned a friend many times and I just talked about the project and I just figure it out on my own. And like the problem is just there wide open. And like I'm maybe talking to someone who doesn't even know engineering and it just comes to me. So if you're like looking at a problem for a long period of time, you might get blind to the project or blind to the problem. Like you're so sure this works, even though it doesn't work, that you just skip right over it. And the friend can help you pinpoint that down. But again, it's nice to have a friend that you can talk to about this stuff. At 4 a.m. in the morning. Okay, so with the time that we have left, we're going to go ahead and perform this activity, which will go ahead and introduce you to developing a project or solving a problem. And this activity is called Mr. Cube's Wild Ride. Fun fact, this was actually the very first engineering activity I've ever done back in my high school, and I'm going to adapt it for our workshop here. So the engineering challenge we're going to do is Mr. Cube, the calibration cube, this is Mr. Cube here, is stuck on top of a mountain. His only way is down is through a zip line. So we're going to use the following materials to create a vehicle for Mr. Cube to safely ride down the electrical zip line. Oh, did I mention the zip line's electrical? It's going to be made out of this wire because I don't have string. So what we're going to do is we're going to go ahead and make a zip line, either through this classroom or down the hall, whatever the case might be. And we're going to go ahead and just, build a device. You're going to build a car using these materials, which we're going to give you. And hopefully your car is going to be designed in such a way that it gets Mr. Cube from the top of the room to the bottom of the room as safely as possible. Now, as of all challenges, we have constraints, things you cannot do. Mr. Cube may not wrap himself up in an enclosure and must easily get in and leave the vehicle. Because it'd be way too easy if you could just crunch up a bunch of paper, put Mr. Cube inside, and have him slide down. You can't do that. You have to make a little cage or a little cart for him to stay on. And you cannot tape him to the vehicle because you must be able to easily remove him at any time. The judge will place him in the vehicle at the start of the competition. So you will not be able to place him in the cage, right? So you can't tape him in. There must be one side open to the air in the vehicle. So you can't, again, create a box. He must be able to fall out. And the vehicle should not exceed the following dimensions. It shouldn't exceed 3 inches by 3 inches by 5 inches, which is pretty small, so don't exceed that. And finally, winning qualifications. You are scored on distance traveled. So if your machine goes down the zip line and stops at a certain interval, that's going to be the distance measured, right? If you get to the very, very bottom, it's going to be then graded on time. So your goal is to get the zip line down to the bottom in the fastest time and for Mr. Cube to not fall out. If Mr. Cube does fall out, you are disqualified because he is dead. And you don't want that to happen. So if the cube falls out mid-flight, no good. You get 30 minutes of planning, executing, testing, troubleshooting, and build time. And then you can have prizes. So the first place will get this squishy TPU cube that I printed. Special squishy Mr. Cube. Orange. And the rest of you can just take Mr. Cube himself home. I have a bunch of calibration cubes in here I usually use for 3D printer testing, so you can just take that home. All right, any questions? So we have, originally this is going to be a team challenge. So Bork, are you going to be participating?
Yeah.
All right, so let's get in teams of 2 to 3. And then we can go ahead and get started. Oh, before we do that, does anyone have any questions for anything I talked about today? Before I end. Yeah.
Does requirement creep always come from within the project?
Does what now?
Requirement creep always come from within the project?
No. Sometimes you're talking with a friend and your friend goes, hey, that's a cool idea. You should implement this extra thing that will cost you time and money and your soul to create. Sometimes it's just because your stuff doesn't work and you have to add an extra requirement. So again,
and sometimes you're designing for a customer.
That's true.
And the customer says something along the lines of, please draw me a 4-sided object. So you draw a square. And they see the square and they go, that's not at all what I wanted. I wanted a parallelogram. So you redraw it, and now it's a parallelogram. And they say, that's not what I wanted. The sides are disproportionate in the opposite direction. So you redraw this parallelogram again, and they say, oh, that is still not what I wanted. I wanted it in orange. And you think I'm being ridiculous by saying that, but I'm not. In the real world, generally, you're designing for a customer. And half the time, the customer does not know what they're asking for, and you have to guide them to the process. Defining your requirements and features is part of the main parts of a project that you will ever do. And if you don't get it solidified early on, you are going to end up with a project that becomes ridiculous.
Yeah. There is a comedy sketch on YouTube. It's something like that, but basically the prompt was to draw 7 red lines that all have right angles to each other or something like that. And it's just ridiculous, but you can Google it. For the most part, a lot of these situations don't actually happen in the real world if you start off with a contract with the customer that says after X amount of time you can't make changes anymore, right? But a lot of times that doesn't happen because the customer will, not sign it. So, but in this presentation we're talking about hobbyist robotics, but that is very true if you ever work in the industry and have to design for a customer. They're kind of annoying like that.
Well, even for robotics projects. Imagine that you're designing a project for school, maybe your senior project, and you present what you've built to your senior advisor. And your senior advisor goes, but why isn't it on wheels? But why doesn't it do it faster?
But why can't it fly up to a power line and charge itself off the power line?
And so now you have to incorporate this for your grade.
Well, that's...
At that point, the senior advisor is acting like the customer.
Oh, yeah. I didn't have to deal with that ever, but, you know, because I'm never threatened by my grade for, like, productivity, like some other projects. That is true, though. So, good points. Okay, let's go ahead and get started. Go ahead and group yourself up into 2 to 3 members each, and I'll go ahead and distribute the parts. She actually did do this before. Okay. All right. See ya, Brayden. Thanks for coming.